Okay, it's starting. From my side, and for now, this is it. I will get back to you at the end of the workshop. I will then give the floor to Andreas or to leave you to start the presentation about wood composites. Thank you.
So I will share my screen. So do you see my screen?
Yes.
Yes. Okay, good. Very well. So I will present the first part today. I have also a different title as Andreas. So I will talk today about overview of wood composites production and properties, identification of opportunities and risks. Let's see. Yes. So before going into more details about the topic of today, a few words about ourselves. So I'm at the Fraunhofer Center HDL in, let's say, beautiful city Bayreuth. Here on the map in Franconia, north of Bayern. We also have groups working in Münchberg, which is a little bit north from here, and in Würzburg. So as Fraunhofer Center, we belong to the Fraunhofer ESC in Würzburg, and we are integrated in the Fraunhofer ESC in Würzburg as part of this institution. And Fraunhofer generally, it's spread all over Germany, and I'm quite sure that Andreas will also have a slide about this, so I will go further, giving a little details about ourselves here in Bayreuth. So you can see here our main building, and here on this side we have the fiber pilot plant, which belongs also to us. We have a technical area in Bayreuth that's around 3,200 square meters. Additionally, in Münchberg, 1,000 square meters, and in Würzburg, a little bit less, so 500 square meters. So our mission as Fraunhofer Center HDL is to design basically energy efficient heating processes and just to contribute to the sustainable technological progress of society. We have a very big group working in developing high temperature materials, high temperature components, as well as high temperature measuring methods. All focus to optimize also the thermal processes. And this is just a general remark for Fraunhofer, not only for us, also for Andreas. Is the primary goal of Fraunhofer is to implement new developments in the industry. Now coming back to our subject, today I will talk about results and the way how we got these results in the framework of the EU project Green Loop. And the Green Loop consortium, it's built by many partners. Here, just this, namely all the partners are shown. And if anyone desire to have more information about this, we have here the site, the internet link, and we are also have presence on LinkedIn, Facebook, and so on. And very important, Green Loop, it's also a member of the Biomatters cluster. So I know that this information will be then, these slides probably they will be available, so you can afterwards have a look on these sites and you can get more informations. What is basically Green Loop? So in Green Loop project, we basically we follow three routes. One route is wood composite bearings for the tool and appliance sector, which I will talk more in details. And we have additionally two other parts in the project. In one we deal with multifunctional rubber panels for the construction sector, and in the third one we follow the development for bottle closures for the food and beverage sector. The work in the project was divided in many work packages, let's say. Us in Fraunhofer, we mainly were involved in work package 5, which is wood composites material production. And how all started? So it started almost 3 years ago when the kickoff meeting took place, and in that meetings we set some values for the composites which we want to produce and how we want to produce it. So we decided that our raw materials should be bio-based, especially wood fibers or particles. We wanted to use biopolymers, and also we knew that time that we will also need fillers to let's say to add some special properties for the wood composites. Also, an important part of the project was to follow the recyclability of the products. Therefore, also with the main aim to reduce the maintenance cost. And also to use some of the inherent advantages of these biomaterials over conventional materials. That is to be 100% regenerative resources, eco-friendly, cost-efficient, and for the parts to use only water or biolubricants. And also, indeed, we concentrate on only some special sector or industry, but we see also great potential for the composites to be used also in other industrial sectors, like building sector, floor plates, transport sector with rollers, and so on. So more detailed about this, we decided that time that we will concentrate on wood composite bearings to be applied in tool industry like injection molded units. So we wanted to produce samples such as rings, cylinders, and half shells. Our partner Guala at that time, the name was Labrenta, provided us with prototype features, design, and so the aim for the end of the project was to produce such wood composite in a small series. And This is a very new thing for such wood composites because this is something which should be used as a precision engineered mechanical component, which till now it's still not really something which is let's say available on the market. So that's about the beginning and how we started. Um, the flow chart for the process was also defined at that time, and um, luckily for us, not many things changed, maybe some few details, but um, basically we started with a chemical optimization for the wood composite. We had an extrusion process for making the materials. And here we indeed were able to enhance the effect of the extrusion with a microwave. And we did the parts, the sample parts using pressing molding. And then we were testing the sliding bearings. Few words about the history basically of wood composites, because some may know, some may not know, but these composites are quite old. They were used even back into the ancient Egypt for making such ships. But let's say they emerged in the 20th century as cost-effective alternatives for the wood materials, as particle boards or MDF. And lately, the VPCs gained popularity in the last, let's say, in the last 50 to 100 years due to his durability. So as application, mainly in construction and furniture, lately also very strong in automotive industry as door panels and dashboards, but also in the outdoor uses. And as definition, wood composites are defined are engineered materials made from wood fibers or particles or veneers combined with adhesives, resins, or polymers. So they have some key characteristics which are presented in this table. Of course, we can use these wood composites to replace some of other technical materials, but we have to agree that not always is it possible to replace solid wood or plastic or metals with a wood composite. Nevertheless, the area of using it's quite large. So knowing all this about wood composites, we had to come up with a solution for making our let's say wood composites bearings. And for this we had to define a recipe for the wood composites. And the key components of wood composites are, as I said, wood fibers, binding agents, and additives. And here in the table, the more or less the percentage how they should be mixed. So we went on the road to look for the best components to use, and we started with looking to for the wood fibers or flowers, which should come from renewable resources, like from managed forest and fast-growing species, or they of course, if they come from this, they should be also biodegradably. Um, and also we were looking at the life cycle impact. And for this, we found a very good partner for us, which did supply us with a lot of wood fibers and flowers, and that is the firm GRS here in Germany. This is just an overview of products which are supplied by GRS, and regarding especially the fibers, cellulose fiber or wood particles and fibers. We had quite a long list of options here. So from this list, we indeed tried some of the options in the composites. And just as an example, two SEM pictures of composites which were made with the arbocell cellulose fibers and wood fibers, and you can see here very clearly here the difference in size and morphology here in these gray areas. Here, this is the cellulose fiber with a very let's say small size, and on the right side you have the big wood fibers where you can even see the structure of the yeah, wood cells inside the composite. Furthermore, we had to decide also about the resin which we will use for making the wood composite. So here the choice was also very big, and also yeah, we looked basically for bio-based polymers, and yeah, it is also very difficult to find uh, the special polymer which we are looking for, mainly because it's a lot of variety of this, and um, also they are you know, the biopolymers are categorized in different categories, like you have um, three major categories of bioplastic. One is biosourced, which is obtained from renewable resources and biodegradable materials. You have a second category, which materials which are made using fossil fuels, oil, and biodegradable resources, and third, that biosourced and sustainable materials, non-biodegradable. Yeah, that also not only the how from which materials the biopolymers are made is important, but also the um, the chemical structure is important. So here in this table is just a list with of let's say with the classical polymers, biopolymers, which can be used for such wood composites. for combining the wood composites and the wood fibers, they come in place also a third category, uh, um, a third part, which are the additives or fillers, and this can be plasticizers, which is an additive to improve the dispersion of filler material in the matrix and prevent aggregation or aggregation of filler material together. This also have an influence on the ductility of the material, and some of the plasticizers usually used, which are shown in the literature. This is the polyethylene glycol, glycerol, or tributyl citrate. There are many important factors which need to be taken into account, like the proportion, how you disperse, and also the fiber surface treatment is important. And here we can have two types of surface treatment. One is physical treatment and one is chemical treatment. So as you can see, it's not trivial to make such wood composites. That therefore we decided to make our life, let's say, a little bit more easy and use already biocomposite, which is available on the market, and uh, further, let's say, improve this biocomposite by adding fillers and additives. So at the beginning of the project, we started with some biocomposites supplied by Stora Enso, which they gave quite, let's say, quite good results. But on the way, we found out that Stora Enso was not anymore producing these biocomposites, so we had to look for alternatives. And one of these alternatives we found in form of Arbo-blend products, which were supplied by the Tecnaro. This is a material which is up to 100% bio-based and contains biopolymers like PHA, PCl, PET, PLA, and so on, and also have already included in the formulation lignin, natural resins, and so on. And with this, we started, basically, we continue our work. So let's say we prepared 3 batches of materials, as I said, based off Stora Enso and lately on the Tecnaro biocomposites. There we added wood fibers from GRS and fillers and additives like recycled glass fibers, which were supplied by the firm STV here in Germany, or lignin from Lignostar. So this is overview of the wood composites mixtures, how we prepare them. So basically, we choose to compound the mixtures in an Irish mixer. Then we perform the extrusion using a classical, let's say, extrusion unit where the barrel is electrical heated, or using microwave supported heating. here down a few words more about this in the next slides. The mixtures obtained through the extrusion process were cut, and then with press molding we got test samples in form of plates, and these were further characterized and machined for special samples for the typological characterization. As I said, a big part of the work was done with our colleagues in Edener to integrate a microwave heating system in the extrusion unit. So here an overview of the unit. You have here the microwave cavity. We have an infrared camera to oversee the heating process. We have the control or the electrical cabinet, and here inside it's the barrel for the extrusion. On this side, you can see the barrel with the electrical heating, and as in the picture, you can notice that it's not the same. This is true. The metallic barrel, which is used in the normal extrusion, is not suitable for the microwave. So for that, we had to develop a new type of barrel made of fiberglass composite. And here in the picture is the first version of it, and in the due to and on the way of in the project we decided to improve this design. Here this is a new fiberglass composite barrel during manufacturing using filament winding. And here on the right side, you can see the new barrel attached to the extrusion unit, but still outside the microwave cavity. So with this, the microwave unit was successful tested, and we also successfully were able to manufacture wood composite with this. Here also a picture of which was taken with infrared camera, showing that everything is working, and with this we were able to produce materials and to test this material tribological for the tribological properties. I think Andreas will show more pictures about these materials. Nevertheless, we were very diligent, and we were also took a lot of time to check the energy consumption. For this, we had help for our partners in the consortium, the IRIS, which provided us with special units to check the energy consumption, and the preliminary results shows us unfortunately not such a big energy saving in regard between conventional heating, extrusion, and microwave heating, which we're using in our prototype. Just one slide regarding the tribological testing. We produced materials here in Fraunhofer, but also NCC, our partners in the project in UK, they also produced materials with or without the microwave assistance, and all of these test specimens were showing very good wear properties, which were indeed also reproduced and confirmed. More about this in the next talk of Andreas. So just a short summary and outlook. Very low friction coefficients were achieved with the wood composites. We had a good wear resistance for this, and we integrated the microwave system and sensoric into the extruder system to reduce the energy consumption, and we were able to produce near net shape wood composite bearings prototypes, which are currently on the way to be testing in industrial environments. And for this, thank you for your attention. And I don't know, either now or after the talk of Andreas, we can have questions and answers. Thank you.
Thank you, Liviu.
So, are there any questions to Liviu? If not, I can. Yes, Giordano.
Hi, thank you very much for the opportunity to talk. The presentation was amazing. The topic is so interesting, and I was just generally curious about the use of a coupling agent. I know the interface is a big issue when we combine such distinct materials, right? So I was wondering if your group has considered to use, let's say, carboxylic acids or other bio-based coupling agents for the sake of producing as green as possible biocomposites, right? Formaldehyde and urea, as you mentioned before, are quite common for this, but we also know the toxicity, and in this sense, that's a drawback when you think in this production, when you look at the green aspect of the matter, right?
So in Green Loop, we were lucky that, let's say, we didn't need to use these coupling agents.
Mm-hmm.
We are currently working in other projects where we will start now to use such coupling agents, because we see that we have some problems mixing the biopolymers and the fibers, let's say. But we are just at the beginning. We have
Sure.
we have indeed to show more, to look more into details about this. I know that these coupling agents can be very difficult to obtain, or I'm not quite sure even if some of them can be, let's say, eco-friendly made. I have to look into it. I do not know yet all the details, let's say.
Sure. Look, I've been working with this area for a good while, so you're more than welcome to contact if you need some, if you want to share some ideas or just to talk. More than glad to support you in your research.
Gladly. You can give me maybe later just a short email with your contact.
Sure, please, by all means. Thank you so much for the opportunity, guys.
Okay. Yeah, I will do that. Yeah, thank you.
My pleasure.
There's one more question from Celeste.
Yeah. Yes.
Hello, good afternoon. Thanks for the interesting work and presentation. I'm here because I'm interested on circular composite materials, but I'm mainly focused on the other type of fibers and materials. But I did a PhD on wood-based composites, so 20 years ago, on medium density fiberboard. And my question today is why you are using extrusion? It's the only way to provide this mixture, because the extrusion here is mainly for the mixture of the components. No?
Yes.
There is not another way for that?
Uh,
The extrusion, also it's a complex process, of course, but also is not bringing some challenges regarding the degradation of the fibers, the temperature degradation, or you didn't see this kind of a problem?
we didn't have the problem with the degradation of the pillars or the wood fibers which we used. The main reason is because we didn't went so high in the temperature.
Mm-hmm.
So this is this was the one reason. The second reason was that we wanted to implement the microwave heating. So that was also the main reason why we chose the extrusion. We were also pre-extrusion. We were using the Irish mixer, which also gave us a pre-mixing.
A solid mixture. Mm-hmm.
Yes, yes. So that was very important for us and showed us very good results. Otherwise, for the moment, at least in our group here, we do not have other options to mix the things.
What I mean.
Yeah.
Okay. So, like Giordano, if I can leave my contact, and I have another idea in mind, so I think maybe it is possible. Yeah.
Yes.
Okay.
Yes.
Thank you.
Welcome.
Thank you again.
Thank you also.
Okay. I think it's time for me to go on with my presentation. I hope you can see it already now.
Yes, we can.
Yes.
Oh, yes. Okay, so you have seen in the first part all production aspects and development of the composites that we have had in the Green Loop project, and I will follow on this with the assessment of these materials for plane bearings or sliding bearings, so for tribological applications. So we looked for some applicability of these materials in not only as a structural material, but also with the functionality for enhanced friction wear properties. And so I will shortly talk about the goals and the materials, but this is very short, and so I think we have not much time. And then concentrate on tribological test results. We had first tests also on lab scale bearing tests, and this I will show and discuss shortly, and then go to a final conclusion and outlook. Just a very short note on our research institute. Fraunhofer Gesellschaft in Germany is quite large, as you have already noticed. We have more than 30,000 employees all over Germany in 76 different institutions. And my institute, IWM, Institute for Mechanics of Materials, is located in the southwest Freiburg. We have here 300 employees and industrial revenues of about 30%. So this is an important figure for us that indicates how well we are working in terms of transfer of scientific results, fundamental results into industrial applications. Our institute has core topic safety and reliability and durability and functionality of materials in different applications, and we have a very large range of methods, experimental or simulation methods, how we characterize and analyze materials in terms of functional behavior in different applications. And one large department of this institute is the tribology department, where we study friction and wear behavior of materials and components. I'm responsible for the group tribological component testing and system analysis. And so we did some quite experimental work within the EU project. So in this value chain that you have already seen, you can see on the very right side, so this bearing, sliding bearing testing demonstration. So here, this is the point where we were active. We looked on friction and wear properties of the different materials and helped to optimize these properties and make these materials fit for bearing applications. I have also to mention that we have, of course, collaborated with Green Loop partners in this project consortium in this work field for the wood composite materials. We have had a very good collaboration with IDENA, which is also the overall project coordinator, NCC, the National Composite Center in Bristol, University Bristol, ISQ in Portugal, Koala Closures, and Iris Technology and Solutions. So I have no time to describe all the work they contributed, but so I'm thankful for this good collaboration, which is still going on. So to the friction and wear aspects, we had at first to define requirements for tribological applications. And here we referred strongly to thermoplastic composites that are broadly in use in such kind of applications. So you can, of course, think of POM, polyoxymethylene, or polyamide, or a PEEK, polyether ketone, or polyimide, and other materials which have a broad range of thermostabilities. With our materials and our matrix, so this beer composites, I think we could meet medium requirements for tribological applications, not the high temperature or high the advanced requirements. But as you can see, we have defined here a compressive strength of 70 megapascals. Wear coefficients was very important. This describes the volume loss per load and sliding distance, which should be lower than 10 to the minus 5. Friction coefficients in dry sliding lower than 0.3. And a so-called PV value, which is a product of contact pressure and sliding velocity, should be larger than 0.3 as an application limit of this material. So they should work within this PV value range up to 0.3 megapascals per meter per second. And temperature stability until up to 100 degrees Celsius. So this were the data we defined, the requirements. We have produced in the project more than 30 different material types in different batches. Also, all of them somehow different in the mixtures of biopolymer, wood fibers, and also glass fibers, and lignin and other additives we have used. And we have produced finally very good material qualities. You can see here dense materials in normal macro photograph and CT, computer tomography images. And on the left-hand side, you can see one of the material types that is still somehow not so homogeneous. Livio also talked about this microwave enhanced processing, and finally with this processing also we got a good material homogeneity and very good mechanical properties, and finally also good friction wear properties, as you will see. The properties here, mechanical properties, here in short, we have had hardness values larger than 50 shore hardness, density 1.2 grams per square cubic centimeter, compressive strengths between 60 and 82 megapascals, and the thermal stability up to 120 degrees Celsius. So very good properties. Not so good was, as expected, tensile strength of a bit lower than 10 megapascals, which is but no problem for tribology, for our application in tribology. And the tensile strength is also rather small here at this point. What we did for tribological evaluation is shown here as a testing method. We used at first a pin-on-disc geometry. We used wood composites as pins, and we purchased rings from bearing manufacturers. So this was the opportunity to buy with a rather small budget a large number of such rings, and so we were very efficient and could conduct a large number of tests with this type of tests. With this type of method, we have used a normal force of 85 newtons, which corresponds once to 3 megapascals, at a sliding velocity of 0.1, which makes this PV value of 0.3. The test duration was normally 6 hours, and we made mostly dry tests without lubricants, which gave the most interesting results. So what we got here as results is shown as an overview on the right-hand side. I always thought it is best to show all the materials in this two-dimensional diagram, where we have on the one axis the friction coefficient, COF is coefficient of friction, and on the other axis the wear coefficient, which is the volume loss in cubic millimeters per sliding distance and normal force. So the lower the values, the better is the material. And you can see in this orange field, we have directly got some materials that show very good friction behavior. So friction coefficient of these materials around 0.15, which is quite low for unlubricated friction. And we have also got wear coefficients in the range of 10 to the minus 5 to 10 to the minus 6. On the right side, you can see here at larger friction coefficients benchmark materials. We have got some materials composed of polyamide filled with fibers and PTFE as friction modifiers, which is very common composition for tribological applications. You can see here the wear coefficients are in the same range, while the friction coefficients of these materials are very considerably higher. So very good for two material types in this first batches. And here we have reproduced these tests with a number of trials where we varied slightly the compositions of the materials, always with a biopolymer and different amounts of wood fibers and also different amounts of glass fibers, and always so in most cases ended up in this very favorable field of very low friction and low wear. So this is very successful. So we have good wear properties and confirmed the low friction values for these selected material compositions. In the next step, then we produced these kinds of bearings. So we have steel shaft material of steel. This is rotating, and we have a radial force between the steel shaft and the wood composite bearings. I think we use about 50 newtons. We will see in a moment. The rotational speeds can be increased to around 3,000 rotations per minute. Temperatures in the range up to 100 degrees. And so these sizes of these bearings were the outer diameter of 60 millimeters. Also, these tests were unlubricated. Here you can see a photograph and the testing geometry as a sketch. And here you can see results on the left-hand side. We used reference materials. So this is not a wood composite, it's a thermoplastic material. And you can see the black and gray curves are the friction coefficients. They started at 0.2 and continuously increased to values above 0.4. And at some certain point, we got catastrophic failure because the friction was so high that the thermal temperature increase was too high for the material, so and then melted down, and the test stopped already before the next speed level was reached. On the right side, you can see wood composite, where we see also here in black a friction coefficient, which started a bit higher, but quickly was reduced to around 0.25 to 0.3, which is not so low as in the pinhole disc test, but really, really good. And you can see also the rotational speed was increased stepwise to 900 rotations per minute, and so the material was stable while the friction was slightly increased in these different speed ramps. So very good friction and wear behavior also in this bearing tests. Just one result for the surface analysis after the test. So we have done, of course, much more analysis, but I think it's not the time, not the moment to show them all. We have seen that on the rings, there is material transfer. So the pin, you can see FTR spectrum of the wood composite, which is in black, and on the ring, on the steel ring in the wear surface, we can see material transfer. So there has been a slight material transfer from the wood composite onto the steel surface, something a small or slight scale, and this enables the low friction as we propose at this moment. Of course, the work is not done at the moment. We are still going on, and we are preparing for component tests for conveyor rolls. Here we have support also from NCC to produce these parts, and these tests will soon be started. So we have time until the end of the project in September this year to finish this production and the final testing as conveyor rolls. And so we are looking forward to final tests and evaluations here. So to shortly conclude, here we have set specifications that was suitable as a guideline for the materials development for tribological applications. We have had very promising results, so the mechanical properties were suitable. We have seen very low friction coefficient without the use of liquid lubricants. We have seen acceptably low wear rates. All important material specifications and requirements have been fulfilled, and we are now looking forward to final evaluation of these materials in conveyor roll tests. So I have still a small evaluation, but I think it's not the time for this. We have already 3 o'clock, so I will close now. And thank you for your attention, and we look forward to questions.
Thank you, Andreas. Thank you for also keeping with the schedule. I guess we can have some time for questions. Meanwhile, I will share my screen with the QR code for the evaluation survey. It's really important for us to know what's your feedback about this workshop. So it will take a couple of minutes to respond. If you can scan the QR code and provide us some feedback on this. Thank you. And once again, if you have any questions, please feel free to raise your hand and ask Livio and Andreas. Okay, then I kindly ask you once again to fill out this survey. Once you do, we thank you for being here, and thank you to the Fraunhofer team for presenting such interesting presentations and developments from the Green Loop project. Once you have responded to the survey, you can leave the meeting. Thank you so much. And keep in touch with the Green Loop platform, especially the LinkedIn profile that we have, because we will have also another external workshop on biorubber value chain. Thank you all.
Thank you very much.
Thank
Have a good
you. Have a good day. Thank you.
Bye-bye.
Thank you. Bye.
Thank you.
Bye.
Bye.
Bye. Thank you.